In the previous module, we introduced white dwarfs as one family of compact stars. So, let us recall some of the salient features of white dwarfs that we have already introduced. White dwarfs are stellar configurations supported against gravity by electron degeneracy pressure. However, there is no energy generation in the interior, but since electron degeneracy pressure is not dependent on the temperature. So, even in absence of energy generation, electron degeneracy pressure is able to provide a long term support to the stellar configuration against gravity. So, you have a stable long lived star as a white dwarf, which does not require energy generation in the interior. And this is a defining feature of compact stars, where you have a long term support without energy generation. The scale and dimension of white dwarfs are roughly, for example, the radius being about 6,000 kilometers for the white dwarf of a mass of 1 solar mass. However, higher mass white dwarfs are smaller in size and lower mass white dwarfs are larger in size. As we saw in the previous module, there is a limiting mass above which white dwarfs cannot exist, and this arises from the form of dependence of the degeneracy pressure changing when the material becomes relativistic, and this limit on the mass of the white dwarfs is called the Chandrasekhar limit, and the value of it is about 1.4 times the mass of the Sun. As you would recall from the previous module, this mass limit was derived using pure degeneracy pressure as the support against gravity and using the Newtonian approximation of the hydrostatic equilibrium equation. Now, in reality, there are other small subtle effects which can change this value of the limiting mass a little bit, and some of these effects is what we will begin by discussing today. So, the corrections to Chandrasekhar mass limit may arise, for example, from the effect of general relativity, from the effect of Coulomb interactions, from rotation as well as magnetic field of the white dwarf. In general relativity, the hydrostatic equilibrium equation that we need to use is given by this, which is the pressure gradient on the right hand side is imbalanced by terms containing the mass plus component of pressure. Density also is augmented by pressure, as well as the term r square now has a correction factor, which is this minus 2 g m by r c square. In case of the Newtonian approximation, we just had g and m, then rho and the r square. So, with this correction, of course, the balance equation changes and you would have the mass radius relation slightly different from what the Newtonian approximation to the hydrostatic equilibrium gives. The m here, m, p, rho, they are all functions of radius r, and m itself is defined as the mass contained within radius r, which is the integral from 0 to r 4 pi r square rho of r dr. This definition is the same as what we have used in the Newtonian approximation. So, this system of equations goes by the name Tolman-Oppenheimer-Volkoff equation, and this Tolman-Oppenheimer-Volkoff equation supplemented by a suitable equation of state. In this case, the degenerate electron equation of state, which is the relation between pressure and density, gives us the equilibrium structure in general relativity. So, let us see what kind of correction general relativity causes to the mass radius relation of white dwarfs. So, here is plotted the mass in the horizontal axis and radius in the vertical axis. There are two lines plotted here. The blue line corresponds to the solution with the full general relativistic equation of state, that is TOV equation, and the red line, which is here, is the old Newtonian solution which Chandrasekhar had used. And you can see that for most part these two lines are practically coincident. So, for most of the masses it makes no difference whether we use either general relativity or Newtonian approximation to gravity to compute the hydrostatic equilibrium of white dwarfs. Here you can see for a white dwarf of 1 solar mass, the radius is about 6,000 kilometers. A small difference does arise when we go to the highest end of the white dwarf mass. In case of Newtonian gravity, you had this 1.44 solar mass as the Chandrasekhar mass limit, and in case of general relativity the curve turns in just a wee bit earlier and the mass limit is slightly reduced. In fact, the reduction in the mass limit is only about 1.4%. So, for most of the white dwarf mass radius sequence, Newtonian approximation is still a very good description of the white dwarf. The next correction that we could talk about is the Coulomb correction to the equation of state of white dwarfs. In the case of the pure Fermi degenerate equation of state, we have not used any information that electrons are negatively charged, the fact that they have a charge at all. All we have used is the fact that they are particles of half integral spin, and therefore, they obey Pauli exclusion principle and produce the degeneracy pressure. However, in a real white dwarf there are electrons which are negatively charged, and then there are equal number of positive charges in the form of ions. And since the distribution of the electrons and ions are not entirely homogeneous in all scales, this creates a Coulomb force between the positive and the negative charges, as well as among the negative charges themselves. So, the fact that the positive charge distribution is not entirely uniform, but it is more like a sequence of point charges which are the ions, and they are arranged in some kind of lattice or semi-lattice structure. So, that creates a residual Coulomb interaction with the electrons and changes the value of the pressure a bit, and this can be computed from the Wigner-Seitz cell formalism, which is a common formalism in condensed matter physics. And since the positive charges are not uniformly distributed, so too are the electrons, the negative charges, and the deviation of electron charge distribution from uniformity and the effect of it on the pressure of the electrons can be computed through Thomas Fermi corrections. And the effect of these two is to lower the pressure compared to the Fermi pressure, that is the pure degeneracy pressure, and the amount of reduction of the pressure depends on the composition. The next figure shows estimate of that. As one can see that for different compositions, helium is on the top, Rn is at the bottom. As you go to heavier and heavier elements, the amount of correction actually increases. What is plotted on the vertical axis is the pressure with Coulomb correction divided by the pressure without it. So, that means the pressure with Coulomb corrections divided by the pure degeneracy pressure as a function of this parameter x. Now, one can see that for small values of x, the correction can be quite large, and for iron, for small values of x, one can see that the actual pressure could be almost half of the electron degeneracy pressure. So, as a result, this has an impact on the radius of a white dwarf for a given mass, because the pressure is now reduced. The radius of the white dwarf of a corresponding mass will also be reduced. White dwarf will be more compact, because if you reduce the pressure, gravity wins a little bit more. So, you need to get more dense to resist gravity by these internal pressures. So, the correction to the mass radius relation can be seen in this diagram. Here again the usual plot of mass on the horizontal axis and radius in the vertical axis. The last line here is the mass radius relation with pure degeneracy pressure without Coulomb corrections, and the solid lines show mass radius relation when Coulomb corrections are included for different compositions. This is for carbon, that is for magnesium, that is for iron, and so on. So, as you can see, as you go to heavier and heavier elements, the correction becomes larger, and for iron one can see that the maximum mass has now come down to almost 1.1 solar mass instead of being at 1.4 solar mass. So, the Coulomb correction clearly is a much bigger correction on the mass radius relation than the general relativity in case of white dwarfs. Coming now to rotation and magnetic field, both in the case of rotation and magnetic field, one would end up with a configuration which is no longer spherically symmetric. They could be axisymmetric, but they will not be spherically symmetric. So, therefore, the formalism we used earlier, either the TOV equation or the Newtonian hydrostatic equilibrium, where we write dP dr and on the right hand side quantities which are only a function of r, can no longer be used to describe these configurations, because now r is not the only variable in the structure. So, appropriate changes will have to be made in the equilibrium conditions, and corresponding results can then be obtained, and people have been doing that for years now. And what we show here are some results from the literature which people have already computed. So, this figure on the left is the white dwarf structure in case where fast rotation is included. So, the rotation, as one can clearly see, tends to flatten the configuration at the poles and extend it at the equator. And because of this additional support from the centrifugal forces, the maximum mass that can be supported with this fast rotating configurations is slightly higher than the 1.44 solar mass Chandrasekhar limit that we have encountered before for spherically symmetric configurations. Now, magnetic field can do something similar. Here we show a result for fully poloidal magnetic field. So, you have magnetic field axis over here, and the equator, magnetic equator is over there, and the magnetic pressure tends to distend the object in the equatorial regions, and so you again end up with a non-spherical configuration. And in this case, you have the equilibrium equation, where you now have to include a Lorentz force term to describe the equilibrium of this structure. In all these cases, one thing that one should always obey, and that is the virial condition, that is the component of these energies added together should go to 0 for stability, just as we saw in case of thermal pressure, thermal kinetic energy plus the gravitational potential energy should sum to 0. So, similar condition now including other forms of energy also have to be taken into account in case of rotational magnetic field. So, once that is done, then you have equilibrium configuration, and we see that if either you have very fast rotation or you have very strong magnetic field, then the maximum mass limit can be enhanced by a certain amount. I will show the result of having a strong magnetic field. So, here this line which goes down like this is the original white dwarf mass radius relation with pure degeneracy pressure in absence of any magnetic field, and these branches which peel off from this and move over, they are the mass radius relations in the presence of strong magnetic field. Each line here corresponds to a fixed value of the magnetic field in the core, and so as you can see, the very strongest magnetic fields that one can use has increased the maximum mass from the 1.4 solar mass here to a significantly larger value to about 1.9 or a little above 1.9 solar mass. But the magnetic fields that are required for such extra support are extremely large, and such strong magnetic fields have never been seen in any real white dwarf. But theoretically speaking, if one has very strong magnetic fields, then one can increase the mass limit in case of poloidal magnetic fields up to about 1.9 solar mass. So, these are the various conditions in which the standard Chandrasekhar limiting mass can be somewhat changed, but nevertheless for most white dwarfs as we see in nature, the Chandrasekhar mass limit still is a very good description of the heaviest white dwarfs that can exist in nature. If we now look at the distribution of masses of the observed white dwarfs, there are many observatories now which have been observing white dwarfs for a very long time and taking a census of their masses whenever those masses can be measured. And this is one of the recent compilations. This histogram, the upper histogram comes from the all the white dwarfs which are detected in Sloan Digital Sky Survey, and this curve shows you that in the observed population, the maximum number of white dwarfs we can detect have a mass close to about 0.6 solar mass. And this distribution has been sort of modeled using 4 component distributions, Gaussian like component distributions, with one near 0.3 solar mass, one near 0.6 solar mass, one near one a little above 0.6 solar mass, and one near 1 solar mass. So, but most of the white dwarfs, about 70%, are in this distribution, which is near 0.6 solar mass, and this one also contains, which is also very near 0.6 solar mass, contains about 23%. So, the most of the almost 90% of the white dwarfs we see are in this region. But there is a tail, and you can see that the tail goes all the way up to almost 1.4 times the mass of the Sun. So, this is what we get when you have a configuration supported by electron degeneracy pressure, and we see that there are defined mass limits, and the mass limit for a non-rotating, non-magnetic white dwarf is close to about 1.4 times the mass of the Sun. What would happen if we now create configurations which go beyond this mass limit? So, let us try to conjecture how the system will behave as you try to go beyond the Chandrasekhar limit. Now, as you have already seen, the larger the mass of the original star, the larger mass is contained in the core region, which is undergoing nuclear burning. So, therefore, the core that will eventually contract and give rise to the compact object is larger for larger original mass of the star. So, for stellar masses which are above 10 times the mass of the Sun, we find that the core nuclear burning is no longer halted by degeneracy, and it proceeds all the way to iron. We have seen in the previous module how degeneracy can interrupt the nuclear burning stages, and the more massive the core, the more stages of nuclear burning it can go through. And if the initial mass of the star is about 10 solar mass or more, then the core mass is high enough, so that all the stages of nuclear burning up to producing iron are executed. Now, once iron is produced in the core, we have also again seen in the previous module that the inert iron core, which is now held by degeneracy pressure, it will keep growing in mass as the surrounding shell sources will start adding their ashes to it. So, just surrounding the iron core, there is a silicon burning shell which is producing iron and adding to the core. So, the core mass will keep on increasing. So, as this continues, eventually the core mass will exceed the Chandrasekhar limit. What will happen then? The core is currently held by electron degeneracy pressure. There is no nuclear burning going on in the core. So, electron degeneracy pressure is the only support available against gravity, but we have added mass to it such that the net mass has now exceeded the Chandrasekhar limit. What would happen? So, it is now too heavy to find pressure support, because degeneracy pressure was the only support available. Now, we have exceeded the maximum capacity of degeneracy pressure. So, therefore, there is no pressure support now. This will then give rise to a rapid gravitational collapse. Gravity wins, and gravity will start pulling matter together, now unimpeded by any other pressure force. The gravitational binding energy that will be released in the process will of course heat up the material. Just as we saw before, when we apply virial theorem, we find that as the core collapses, it gets hotter, and if the collapse is very quick, heating will also be very quick. And this quick heating will generate a lot of radiation in the interior, and this radiation will start interacting with the nuclei which have been already produced, and it will lead to photo dissociation of these nuclei. So, see, all this period of stellar evolution starting from hydrogen burning has gone into creating heavier and heavier and heavier nuclei by nuclear fusion. Now, in one stroke, as the final gravitational collapse occurs, photo dissociation is going to undo all this work of nuclear burning, and it will now dissociate all these nuclei into their components. Now, as the photo dissociation occurs, simultaneously one will also find that the electrons which are present in that same volume are getting squeezed even tighter, and as they get squeezed even tighter, their Fermi energy and the Fermi momentum will continue to rise, and it can rise so much that it may become unviable for them to remain as free electrons rather than being captured by protons and neutrons being formed. And this capture then starts happening in earnest as the rapid gravitational collapse proceeds to very high densities. So, this process where electron is captured into protons is called the inverse beta decay or neutronization of matter. The process is schematically explained in the diagram here on the left. So, we have at lower densities, if you have a neutron, if we have a free neutron and leave it in space, the neutron decays into a proton and an electron and an antineutrino. And that is because the rest mass of the neutron is larger than the sum of the rest masses of the proton and the electron and the neutrino. So, going from neutron to proton plus electrons plus neutrino is in fact a lower energy state, and it prefers to do that. So, if the density is low, then you have the neutron rest mass giving you the net total energy there, the proton rest mass which is lower than the neutron rest mass giving you a certain amount of energy here, plus the electron has its own rest mass which is much smaller than the proton rest mass, but it may have some Fermi energy. So, the total energy, the rest mass plus Fermi energy is somewhere here, and these two sum together, as long as the total is still less than the neutron rest mass, the neutron will prefer to decay and produce proton and electron and an antineutrino. However, as we go to higher and higher densities, we find that the electron Fermi energy will begin to rise. We saw that the Fermi momentum of the electron increases as number density to the power of 1/3. So, as you go to higher and higher densities, the electron Fermi momentum will increase and correspondingly the electron Fermi energy will increase. So, now at some point the sum of the electron Fermi energy plus the proton rest energy can go above the neutron rest mass. If that happens, then the transition the other way will be preferred. So, the electron and the proton will combine now to form a neutron and release a neutrino. So, this is what happens when you squeeze matter too much, you go to high densities, raise the electron Fermi energy, and you then get capture of electron onto protons producing neutrons. So, this is what we call neutronization of matter. As you go through this combination of protons and electrons, clearly the number of electrons will now begin to go down. As the number of electrons goes down, the number density of electrons will also reduce, and the electron Fermi energy will then correspondingly begin to reduce. So, a balance will then occur when the electron Fermi energy drops to a level, so that the net effect of inverse beta decay and the forward beta decay are balanced, and you do not have any net energetic favorability going from in one direction or the other. So, that will then decide how many electrons are left and therefore, how many protons are left, because for charge neutrality you need to have the same number of electrons and protons in the mixture. So, this added to what we call picnonuclear reactions, where at high density two nuclei can combine to produce a heavier nucleus. So, this plus electron capture then will keep changing the composition of the material, because as you change the number of protons in a material and create more neutrons, of course, both the atomic number and the mass number will keep changing. and ultimately you will get what is called the cold catalyzed nuclear matter, where the matter is in beta equilibrium, where the chemical potential of neutrons is equal to the chemical potential of the protons plus the chemical potential of the electrons, where chemical potential itself is defined as the square root of p f squared c squared plus m squared c 4. The equilibrium nuclear composition may then be derived by combining with nuclear mass formula including shell effects, and people have arrived at this diagram which I show here, where the ratio of mass number to atomic number is plotted against density for densities going up to about 10 to the power of 12 grams per cubic centimeter, and you can see that A by Z begins to rise as you go to higher and higher densities. So, this means that the material, as A by Z rises, the material is getting more and more neutron rich. In regular terrestrial matter, A by Z is roughly about 2, but here as you can see, as you go to higher and higher densities, it has risen well beyond 2, and if you go to even higher densities, this will rise even further. So, now let us take a look at the consequence of this process. So, as the electron capture proceeds, the matter now becomes progressively neutron rich. Now, remember, electrons were providing the degeneracy pressure, which was holding up the star before the mass exceeded the Chandrasekhar limit. So, once the collapse starts, the electron degeneracy pressure is still there, but the electron capture removes electrons from the system and further depletes the electron degeneracy pressure. So, now even whatever little pressure was there, that pressure itself disappears because the electrons disappear. So, now gravity becomes even more unimpeded, and density rises very rapidly, until halted again, but by some other forces. It is no longer electron degeneracy pressure, but now these are the nuclear forces. So, as the matter reaches almost nuclear density, then you find one more level of support against gravity, and this configuration, which now has mostly neutrons, because electrons have been captured by protons and formed neutrons. So, therefore, these configurations are called neutron stars. So, once the matter exceeded the mass of the core exceeded Chandrasekhar limit, it just quickly collapsed, and eventually the collapse will be halted when a neutron star is produced. Now, such neutron stars also have an upper mass limit. It is somewhere around 2.5 times the mass of the sun. We do not know the exact value. The exact value is not known because the nature of the nuclear forces at such high densities is yet to be determined. And this is one of the very important fundamental physics questions that a lot of people are trying to address, and the study of neutron stars is one of the interesting ways of addressing this fundamental physics question. We will come to the more of that during our future lectures and modules. The collapsing core has a certain mass. It is obviously more than 1.4 solar mass, but it could have a mass which is even higher than that. Now, if the collapsing core happens to have a mass larger than the neutron star's upper mass limit, then even this nuclear forces, the forces between neutrons, will not be sufficient to halt the collapse against gravity. So, what will happen? What we know today is that there is no other force which can then halt it before the whole core has collapsed irretrievably and entered the state of a black hole. So, if the collapsing core has a mass higher than this neutron star upper mass limit, then most likely a black hole will form. Now, this entire process of starting from the exceeding the Chandrasekhar limit by adding of mass to the iron core to the final collapse is in fact a surprisingly quick process. And this is because the dynamical time scale of this very dense configuration is really only a few seconds, and the whole collapse happens in this dynamical time scale. The energy released in this process is enormous, because you come from a very distended configuration to a very, very compact configuration, and the entire gravitational binding energy is released. So, this very large amount of energy is released in a very short amount of time, and this causes the envelope in this case to be ejected explosively. Remember, in the case of white dwarfs, the envelope was ejected gently and a planetary nebula was formed. In this case, there will be no such gentle process, but the envelope will be really ejected explosively with very high energy, and this will give rise to events like supernovae or gamma ray bursts. So, supernova is an event which is then triggered by the core collapse of a massive star. This is an animation created by NASA. So, we are taking here a trip inside the star. You can see that this is the burning core, and inside the burning core you will have other stages of nuclear burning. You have shell burning, and then further stages of nuclear burning happening at the center, and finally, the iron core is produced. It then collapses, and you have a very bright explosion, and you see this material ejected explosively, and at the center what is shown here as a flashing object is a compact neutron star left. So, a compact object is left behind at the center. So, to trace the star's journey to a supernova, then we started with hydrogen burning, which is the first stage of nuclear burning and which is the longest stage in a star's life. Then once the hydrogen burning in the core is concluded, the track moves diagonally upwards in this density temperature diagram. Two tracks are shown here, one is for 25 times the mass of the sun, one is for 15 times the mass of the sun as the mass of the original star. The core mass is of course a small fraction of it. Then the core goes through helium burning, then carbon burning, then oxygen burning, silicon burning, and finally producing iron over here. And as the iron is produced, you then have no further burning, the iron core grows in mass, and once the mass grows beyond Chandrasekhar limit, you will then find the core collapsing and giving rise to a supernova. So, this core collapse supernovae, this simple energetic numbers are like the following. The total energy that is released in the process is about 10 to the power of 53 ergs, most of which is actually carried away by neutrinos generated in the process. The envelope is ejected with a kinetic energy which is of the order of about 10 to the power of 51 ergs, and the amount of radiation produced which we see in this from this explosion is about 10 to the power of 49 ergs. Now, if the star is massive, then the core size which is collapsing is likely to go beyond the upper mass limit of neutron stars, and therefore directly form a black hole. And usually these cores are also spinning very rapidly. So, these massive fast spinning stars will produce black holes at the center, and as the matter then converges on it from the stellar envelope, that matter can extract some of this rotational energy and be ejected in the form of a very fast moving jet. So, this jets can get up to very high speeds with Lorentz factors of the order of hundreds, and if you happen to be looking, if your line of sight happens to be along one of these jets, then you will see a very bright gamma ray flash, and those are what we call the gamma ray bursts. Now, this process of core collapse supernovae also produces rapid nucleosynthesis by fast moving neutrons being captured by the material that is being ejected, and large number of neutrons are captured one after another, and by that the mass number of the nucleus is changed dramatically, and then the nucleus undergoes beta decay, and in the process of beta decay it then produces various stable elements which are much heavier than the iron that was initially produced in the stellar core. So, the source of heavy elements beyond iron, one of the major sources is this supernovae. So, the source of heavy elements in the universe are primarily the supernovae. So, as the core collapses, here this diagram summarizes the different stages of that process. The core, it goes through a inward movement, which is the collapse, and at the center suddenly the density at some point rises enough to halt the collapse. This is due to nuclear forces, and as the collapse is halted, a shock wave is sent back through the material converging onto it. Some of the matter crosses the shock wave and converges onto the center, but some of the matter is turned around by this shock wave and also by the neutrinos which are being emitted by this, by being absorbed by the envelope. The material is turned around and an explosive ejection takes place. So, that is how this core collapse and bounce leads to the very energetic supernova explosions. Here is a real picture of a remnant of such an event. All this blobby material that you see is actually the material ejected from the envelope of the star, and at the center there is a bright neutron star which is located at the site where the explosion occurred. This picture is taken in X-rays by the Chandra X-ray Observatory. So, you have at the center now neutron stars. The neutron stars are supported by a combination of neutron degeneracy pressure and repulsive strong interaction. Using TOV equation and the nuclear equation of state, one can then describe the structure of these stars. The material there is in beta equilibrium. The beta equilibrium requires that almost 90% or more of the material is neutrons, and only less than 10% matter is in protons and electrons. However, we still have some uncertainty in the knowledge of nuclear equation of state, and that leads to uncertainty in the prediction of mass radius relation as well as the limiting mass of neutron stars. Now, upon exceeding the maximum neutron star mass, a black hole would actually result. Now, in this neutron stars, we have internucleon distance which is about 1 Fermi. That is when nuclear forces become dominant. So, if you have internuclear distance of about 1 Fermi, that gives you the estimate of number density which is about 10 to the power of 39, and therefore, if you have nucleons with this kind of number density, that gives you a mass density of about 10 to the power of 15 grams per cubic centimeter. With that density, a solar mass object will have a radius of only 10 kilometers. So, now going through these different stages, when the star was thermally supported, a star of size about 1 solar mass will have a size of about 1 solar radius, which is 1,000,000 kilometers. If 1 solar mass had to be held by electron degeneracy pressure as a white dwarf, the size would be about few thousand kilometers, 6,000 kilometers or so. If 1 solar mass star has to be supported as a neutron star, then its radius will be only 10 kilometers. However, as you have seen that to produce a neutron star, you would have to go through this barrier of Chandrasekhar mass limit. So, the baryonic mass of a neutron star will typically be 1.4 solar mass or larger, because it required that much mass to start collapsing in the first place. The gravitational mass after the collapse will be about 1.25 solar mass or larger, and the difference between the gravitational mass and the baryonic mass is the gravitational binding energy that is lost in the process. We also know that neutron stars actually spin very fast. The spin periods of neutron stars are known to be in the range of few milliseconds to few minutes, and they also have strong magnetic fields in the range 10 to the power 8 to about 10 to the power 15 Gauss. So, these give rise to exotic phenomena like pulsars, magnetar activity and so on, which we will cover in some of our future modules. One thing we must realize that for describing neutron star structure, GR is essential. Unlike the white dwarf case, where we found GR made a small difference in the mass radius relation, in case of neutron star, if you did not use GR, we will get a completely wrong mass radius relation. And this is what is shown here in this diagram. For a given equation of state, you take GR into account, and this red line shows the mass radius relation you would get taking GR into account using TOV equation. Instead, if you had used just the Newtonian approximation to the hydrostatic equilibrium equation, you will get this blue line. So, this is completely different from what the TOV equation tells you. So, therefore, the TOV equation is the right thing to use for describing neutron star structure. It is also important to see that the nuclear forces are an integral part of providing support to the neutron star. If we just use the neutron degeneracy alone, then using TOV equation, the mass radius relation that you will get is this, and the maximum mass that neutron degeneracy alone can hold up is only about 0.7 times the mass of the sun. But as we have already discussed, the route to formation of neutron stars will ensure that this collapse can only proceed to neutron star stage if the mass is already about 1.4 solar mass or so. So, for realistic neutron stars, neutron degeneracy pressure alone is not sufficient to provide balance. So, in realistic neutron stars then, nucleons are squeezed within interparticle distance of about 1 Fermi, and if you look at the internucleon forces, they are attractive at slightly longer distances, and when you come very, very close below 1 Fermi, the interaction becomes repulsive, and this repulsive interaction then provides a force, sustaining force against gravity. So, strong nuclear forces become important contributor to the equation of state when you squeeze it to near nuclear densities, and the nature of this force, basically the slope of this line, is still not very well determined. So, therefore, the nature of this force is still a little uncertain, hence there is an uncertainty in the equation of state. So, the repulsive strong forces raise the upper mass limit beyond what the neutron degeneracy alone could provide, and thus hold up realistic neutron stars. What is the kind of masses they can hold up? So, as I said, there is some uncertainty in the equation of state, and therefore, that uncertainty corresponds then to uncertainty in the mass radius relation. So, there is various lines here for various descriptions of the equation of state, and you can see these go up to about 2 to 2.5 solar mass as the maximum limit. So, that is where one feels that the maximum mass limit of the neutron star in whichever equation of state you assume is somewhere around 2.5 times the mass of the sun. If the mass of the core had actually exceeded that, then you would have had a direct formation of a stellar mass black hole. And in addition to the supernova which would have occurred in this collapse process, the black hole formation also gives rise to fast moving jets because of fast rotation and material trying to accrete onto the black hole at the center. So, this fast spinning disk, which is short lived, gives rise to a short lived but powerful relativistically expanding jet. If our view axis lies along the jet, then we see a very bright flash of gamma rays, and that is what we call gamma ray bursts. So, we have now seen that as far as compact objects go, we have talked about 3 different families. One is white dwarfs, which are held by electron degeneracy pressure. Another is neutron stars, which are held by a combination of neutron degeneracy pressure and nuclear forces. And if there is no support available, then the core collapses to form black holes. What is shown in this diagram is the range of different stellar masses which lead to this kind of different outcomes at the end of their evolution. The diagram on the right is a famous diagram called the Hertzsprung-Russell diagram, where effective temperature is plotted on the horizontal axis and the luminosity of the star is plotted on the vertical axis. And most of the stars we see in the sky lie on this red line, which is called the main sequence, and they are all burning hydrogen. And for each such star, after the hydrogen burning is over, the evolution follows one of these tracks, and at the end of this track is where the compact object is produced. Now, this schematic diagram here shows the range of stars which will then lead to different types of outcomes. You have white dwarfs starting at small masses, going all the way up to about 8 or 9 solar mass as the maximum mass. If the initial mass of the star was about 9 solar mass or so, you still have a white dwarf as an end product. If the initial mass of the star was higher than that, then you will produce neutron stars up to about 40 solar mass, after which the stellar collapse will produce black holes. If we take a census in our galaxy, the total number of stars is about 10 to the power of 11, and the white dwarfs which are already been have already been produced number about 10 to the power of 10. Neutron stars are about 10 to the power of 8 or 10 to the power of 9, and number of black holes is about 10 to the power of 8. So, this is what we have in our galaxy, and every galaxy have similar numbers. So, this is our census of the compact objects that we are talking about in our galaxy as well as in the universe.